really simple and kind of a very lazy, but like ultimately effective in the same way as a sledgehammer way. And it's eagerly distributed. And what I mean by that is that when nodes get near each other, they very aggressively seek each other out and then try and exchange as much information as humanly possible. The idea being to spread a large coherent knowledge graph over as many nodes as possible, each with their own redundant local copy. And so originally it really was just like I was frustrated by Jira, I think, and I wanted an offline copy of it. And then I went down the data structure rabbit hole of like, what can I do with this thing? And then I wanted to sync my copy with other people in the office, and everything got way out of hand. But people are actually using it for things now, which is amazing and terrifying. So one of them is Project Byzantium, who are working on like a live disk distro that basically, like if you're in a disaster-affected area, you slam this thing into your computer and your laptop forms a mesh with everyone else. So centralized infrastructure not being there isn't an issue. And so they built a distributed bulletin board out of it. So you can post messages, and just by going near people, you actually exchange that information. And so in spite of the fact that I haven't explained what I'm doing or why, I'm actually going to demo it now, because what I did at 3 o'clock this morning was just like cripple the bitrate to at least guarantee that data will get to the other end. And as a result, my demo is going to take the whole talk to finish. It's all right though, because it's not. Anyway, before I do that though, I'm going to be using some pretty high frequency sound. So is anyone here like really sensitive to sound at around about the 19K mark? Because that would be bad. Sorry? You do have a dog? Oh, all right. You're good. If you can speak, yeah, we're fine. All right, cool. So now, like, tell me whether or not you can. Is that like somewhat readable maybe? Yeah. Cool. And so what this does is it basically starts a listener, listening at 19.1K, which is literally a magic number that I pulled from someone else's project that seems to work very well. No idea why. And so on my other machine, I'm starting the client. And basically all this client is doing is like iterating through all of the elements in its graph database, serializing them into a bit stream, transmitting the bit stream, and then this end unpacks them and then displays them. And already it's like experiencing severe corruption, and all the work I did this morning was to waste. Anyway, it actually does correct itself with like somewhat reasonable guarantees. So I'm just going to let this run while I give the rest of the talk. I deliberately kind of made time to like check in on it later, and we'll see whether or not it's actually coming good. Yeah, fingers crossed. Live demos are the best. So yeah, it's finally starting to pull through some header data, and it's like gradually unpacking it. Cool, so back to the topic at hand. Oh yeah, this slide was relevant. So let's talk about DAGs. A DAG is a directed acyclic graph, or a snatch reference. And so who here has used Git? Cool, nearly everyone. You've all used DAGs. The three interesting properties are, like the graph thing is fairly self-explanatory. The directed element is basically that of the graph composed of nodes and edges, the edges traverse one node to the other, and the way that they do that is that one node actually contains all of the names of the nodes that it has edges to. And acyclic just means that you can never have like a loop in it. And technically, like that is possible in Git. It's just incredibly difficult to arrange, and it'll hopefully be a very long time before anyone does. And so this is what a DAG looks like in kind of like Git land, where you would have played with it before. These should be arrows, but drawing graphs in Keynote sucks, and I was not going back. So basically the way this works is that at the top you've got a source of truth. So you have like a commit hash, or the name of an object. And then it traverses through a bunch of nodes, and then eventually you wind up like at an object that has no parents, and that is the entirety of this graph segment. And so the interesting properties, particularly of Git, but of Groundstation as well, because I'm using its ODB, are that because everything is immutable, like this graph can never change. Like this is like a fixed point in the universe, and while I can add stuff to the top by adding new nodes to the top that then like name other elements, so I can make this graph bigger, but this graph will always be a subset of any graph that I add to it, and this graph will never change. And that's enforced by a second property called content addressability. And so all content addressability is if you take some datum and then you hash it via some process, I'm using Git's ODB, so it's SHA-1, and then you just name it that thing. you can trivially check whether or not some object, so then when you try to retrieve that object from the database, you can trivially check whether or not you've got the right one, because you just hash it, and if it has a different hash than the name you asked for, something bad is happening, someone's messing with you, your disk is going bad, something, whatever. But so the cool properties about this are basically that you can sync these in really, really silly ways. Like if you're syncing a traditional database, you need to check that you have isolation and atomicity and consistency and a bunch of other stuff that sounds really, really hard. Instead, with content addressable immutable objects, you literally just give people content and tell them to write it into their database, and it'll come out in the wash. And if they get it wrong, it will actually sidestep the graph and not wind up in it. So if you just keep giving it to them over and over again, eventually they'll get a good copy and the graph will come together. However, because of the way Groundstation works, when you're aggressively giving people data and you have no notion of locking or a single point of truth, it's not reasonable. So the thing I forgot to mention is that this single point of truth has to be absolute. You can only have one point that represents a graph in Git's hash chain implementation. Whereas I very deliberately didn't want that because all of my applications were meant to be incredibly asynchronous, potentially not happening on the same network or the same country, and so needing to coordinate with your peers to add stuff to the graph was really, really impractical. And so what I did instead was I just arbitrarily decided that I would not use the same format. And instead, I represent a source of truth inside the Groundstation database as being a set of points. And so if you add a new node to the top of the graph, you can safely purge the node that used to represent the tip from the source of truth because it's now a part of the graph. But if you're going off in a different direction, you just add your thing, and then when you sync it up, you just loop them all in and treat that as a single source of truth. Now, this really sucks for anything like source code or an actual database or all kinds of things that you actually do need a single consistent point and you don't want to rely on computers to awkwardly try and merge. But for most of the fairly soft applications I had for this, a bulletin board is actually really, really easy to express as a set of points. You just branch the conversation at the literal point the conversation branched and then show it to a user and let them work it out. And so that's basically what I did. Yeah. I'm not going to do I've got this database set up. I made these screenshots last night, but trying to Chrome across the other thing that I can't see is a pain. So basically, this is what the interface looks like. I'm a terrible designer. But so basically, the important thing is that you can see the point on that graph diagram on the right. You can see that it's actually diverged. Two people added nodes to the graph that couldn't see each other at the time. But looking at this, you have no way of telling which node was inserted first, or even which one is which. And so in my shitty designer glory, I decided that I would just if you click on one branch, it will just color that branch in separately. And this kind of makes more sense with a more complicated graph, but unfortunately size constraints. And so conversely, you get the other thing. So if you click the other side, it'll just highlight that side. So you can explore the conversation in a fairly organic, albeit really ugly way. And then finally, if you reply to a node, the assumption is that you actually were replying to everything visible. So in this instance, it's merged that diverged graph back into a single point. And so the way this works under the hood is three discrete components. You have a protocol driver, which is responsible for doing stuff that the user can see. So for example, that application is actually called Airship. It's a silly metaphor. So the protocol driver is responsible for unpacking and rendering the markdown inside of the objects, working out how to present them on the graph, working out how to show them to the user, working out what the relationship between objects actually is, and then managing the internal data structures. There's the object graph that I talked about already, which is basically just this DAG structure of nodes that can have this superposition of multiple points as a source of truth. And then the transport driver, which is where I'm slowly getting to in this talk, which is given that I have these data structures, how do I get them to other people? And so I'm going to kind of skip over this because we're running short on time. Originally, I was concerned that I didn't time my talk, but I think we're good. So one of the interesting things, though, is the fact that because I'm using Git under the hood, all of the Groundstation specific stuff is actually just using blobs with magic contents that Groundstation knows how to deal with, or rather that protocol drivers know how to deal with. But it doesn't actually know how to move about the entirety of a Git database. So there's no reason that you couldn't actually sync source code using audio waves, apart from sanity and reason. But so one of the other really interesting ideas that someone posed to me that I haven't really looked into yet was a decentralized marketplace. So some kind of a Silk Road-esque thing, not that I would necessarily encourage it, but instead of like relying on onion routing or like internet infrastructure at large, why not have a database that literally is only accessible to people who are physically proximate to it by virtue of the fact that you need to get near someone in order to grab that section of the graph. So anyway, I already talked a little bit about how the object graph works. I'll go into like a tiny bit more detail, but it's not super important. So basically you have root objects. And as I mentioned, everything in the database is content addressable, meaning that if two people hash identical objects, they'll wind up with literally the same object with the same name. Meaning that, so for example, if two people are pulling in data from some third party, and as long as you organize that the root object contains very little state, two people doing the same task will actually wind up with the same graph, and then when you sync them, it'll effectively dedupe. So the purpose of a root object isn't actually to carry any data. All it does is basically act as a placeholder with a tiny little bit of metadata in it, like basically optimizing for collisions. Update objects are the things that actually carry like data that's presentable in some way, whether that be like git commits, messages on the message board, whatever it may be. And then gref tips, so I'm really creative. Git has refs, Groundstation has grefs. And so gref tips represent basically the tips of the graph that are like the part that you should start walking at when you want to present whatever data is in the graph. So the original transport driver is kind of like where we're getting to the meat of this thing. And so the first transport driver was really, really silly, but like ultimately it worked pretty well. The assumption was that you're on a more or less homogeneous link layer network. And so all the nodes do is they shriek UDP traffic onto the network in order to find one another, and then when they find their peers, they connect to them with TCP and proceed to like exchange objects very, very aggressively. And there's a little bit of magic in it for basically like once you know about a peer, if you get more stuff, you can reach out to them to give it to them. But the gist of it is really quite simple. It's basically like make a ton of noise so that people can find you, and then when they find you, aggressively give them everything in your database. Which kind of brings me to the data distribution strategy, which is like always try and give people as much state as humanly possible, because ideally you want like as much world state as humanly possible. And there's like some optimizations that you can do later for like probabilistically forgetting things in such a way that like everything is probably still on the graph. But like luckily, I guess, it really just hasn't seen enough adoption that like too much data has been a problem yet. So for the time being, just like shoving all of the data that you can find across to your peers is working just fine. And so here's like the first, let's see whether or not this has failed miserably yet slide. Okay, so it's, there is a fair bit of corruption. But basically like it's successfully like locating, it's nearly gotten to the end of a byte. It's nearly gotten to the end of a message. If you scroll up a little bit, it was expecting something in the order of, I think, 100, oh, right. Let's just start again and hope for the best. Is my current plan. I deliberately timed this so we'd have like a few stabs at it. Turns out audio is actually a really bad transport layer. Who knew? Cool. So like practical applications. I touched on Byzantium using it for disaster-affected areas. And for them, it's actually a really valuable tool. Like, I think it was the hurricane in the Philippines that it was actually deployed in, which blew my mind because I'd only just finished writing this at the time, and I couldn't believe people were actually using it. But in that case, like if you imagine someone who's in like a city or like a small town with very little centralized infrastructure that's taken out by like a flood or a cyclone or whatever, and there's a message board with people posting like what they have, what they need, whether or not they're okay, and like who they're looking for in like their family members. And so someone like takes their machine to like a town hall or whatever, grabs the whole graph, and then drives 40 kilometers to like the next town. If the next town also has Groundstation nodes, they will basically grab the entirety of the message board state from the other town and then have that context. And that actually can be a really huge deal in some cases. In more esoteric forms, because it works really well with Git. I used to work at 99 Designs, and when I was there, like nearly all of the devs ran Groundstation nodes. And basically, like as you added data to the Git database, it would sync across everyone in the office, and it basically made Git fetch and no-op, because all it had to do was update refs from GitHub, which is way at the other end of the scale, but it's satisfying every time I do it. So I already talked a little bit about like kind of other stuff that you could do with it. Painless sneaker-nets is kind of where I'm getting towards with this. But like all of the transport drivers assume physical proximity. It actually does have support now for internet routing, but you need to already know the address of your peer and a bunch of context. It kind of sucks. It's really only good for a congregation point if you're using it very aggressively. I mean, like, wireless is really, really easy, and like, it does a lot of the right things. Byzantium took a lot of the pain out of it, providing that you're willing to like boot their live disk. But like needing an 802.11 stack is kind of shit. Like, not all laptops have it. Not all laptops have good drivers for it. Sometimes you're attached to a network that wants to filter UDP broadcast traffic because some idiot might shout really, really loudly from all of his machines at the same time. So let's talk about air gaps. You're getting back to the red BIOS thing. Sorry, I kill myself. So Quietnet, which I touched on from Katie, this is basically like a simplex channel that will basically let you transmit data from one machine to another very, very lossily, both in terms of like just dropping packets on the floor and also in terms of like you get tons and tons of bit errors, you get random garbage spat out to your terminal. Every now and again you get super lucky, you get some escape codes that changes the encoding of your terminal. Everything kind of sucks. The upshot is that it's actually like really simple to understand. Before I picked up this project, audio was all voodoo to me. I mean, it still is, but less. But like most of the like proper projects, like GNU Radio, for example, which is amazing, but like the learning curve is a cliff, and like you fall off it, not go up. And so, thank you. But so like Quietnet was basically written by someone who was like trying to work out how to audio, and I'm like really impatient and love instant gratification. So I was really excited about the prospect of just like picking up a thing and then just like smushing it into my use case. But like it was like really well commented and functions had same names and there wasn't a bunch of like, I mean, there's a ton of math in it, but it's not just like arbitrary math because it should be intuitively obvious to you that this is how you FFT or whatever it may be. It's, like, and especially in the commit log, it's very obvious like how everything fits together. And as a result, it was like super easy to hack on and at least like build a prototype with. So like, let's talk about encoding, which is everyone's favorite thing, because normally when people say this, they're thinking about like Unicode and the ASCII debacle. But in this instance, it's literally just that like, given some piece of my knowledge graph, I need to turn it into a series of bits in order to like send it across any network. I mean, like, luckily, the BSD socket API makes that kind of simple when you're talking on top of like a very high level abstraction. But if you're using something like a serial console or audio waves, you need some coherent mechanism for turning it into a bit stream and back. And so in Quietnet, Katie used PSK31, which is a standardized frequency shift keying scheme. And so one of the things that's really interesting about it, it looks a little bit like Morse code. And actually, I assumed that it was when I first saw it, but on closer inspection, it's not, and I'm an idiot. But so the interesting thing here is all of the codes begin and end with a 1, and there are no repeated zeros in them. And the reason for this is that it has a sigil that delimitates messages, which is 2 zeros in a row. And assuming that you have like no bit errors on the wire, this is like really quite efficient. If the reason I picked this section of the graph is that you can see that the vowels have much shorter encodings than like the letters that aren't used as often in the alphabet, which means that like the letters you're most likely to use occupy less space on the wire, and it packs up pretty effectively. Unfortunately, like bit errors exist and terrible things happen, and as a result, like it's bad. It's not a great encoding scheme unless like loss is okay. Like for clarity, if you're like encoding text messages and you're not trying to process them digitally and you're just trying to like print them on paper to give to someone, yeah, like missing characters or like the occasional character that like bit flips and an A becomes an N, like whatever, it's fine. Not so good if you plan to hash that object and then store it by that hash, because nothing will ever line up again. So there's this great thing called an error correcting code or a Hamming code. And so I picked these 4 sequences fairly arbitrarily. They're actually buried in the depths of Groundstation in kind of an awkward way at the moment that's not fully utilized because it is actually so much data that my demo would have taken most of today. But so the interesting thing about these codes is that you can flip any 2 bits in any one of these 4 sequences and still unambiguously decode it. And the reason for that is that all of these bit strings are 3 bits apart from each other. And so what this means is that if you're transmitting over a really, really lossy link, bit errors are really not a problem for you, unless it's like so lossy that more than 30% of your bits get flipped, in which case you're probably toast. And so I mentioned that this came up at ShmooCon this year. So Dominic Spill and Michael Ossmann presented their work on unambiguous encapsulation. And like, I'm not going to go too far into it. The talk is on YouTube. It's really amazing. You should definitely check it out. It was their mitigation for Travis Goodspeed's packet-in-packet attack. But one of the cool things about this was the basic idea is that instead of having these instead of having these 4-bit strings, you have 2 groups of 2-bit strings. And while each of the ones inside of the inner ovals is 2 bits apart, the 2 ovals are actually 3 bits apart. So even if you get so many bit errors that like your internal data gets munged, it's impossible to misparse like, so for example, if you use the top code to encode header data and the bottom code to encode payload data, it's impossible to accidentally misparse header as payload and vice versa. And particularly if you know what you're expecting, it gives you a really good way of like trying to work out whether or not terrible things are happening. Which is why when we checked in on my demo that's not looking so great, there were so many error messages saying like I got header data when I was expecting payload data. The reason for that is that it was encoded in the wrong way, and hopefully when this just like retries, like I said, it just like yells all the objects. Hopefully the next time the same bits won't flip, and we'll get away with it. And so here is where this turns into a fail talk. So originally, like Groundstation had this cool TCP driver that like knew how to sync things up, and it was pretty fast. It wasn't super efficient, but it was really easy to debug. It was like really easy to pull apart in Wireshark, which was important to me. And so I basically just thought like, how hard can audio streams be? I'm just going to open like a full duplex connection and then just like literally just wrap it with a BSD sockets API, and it'll just sync up and it'll be done. I'm going to be out of here like by this afternoon. That's not a thing. Yeah. It sort of is a thing. It is possible to make it work in a perfectly silent room. As I discovered, it also needs to be the exact same shape and size as my bedroom. At the moment, I actually haven't got the latest code out. It really desperately needs a rebase. Like, I don't want to publish the shit show that it currently looks like. When I publish the demos, like, I totally encourage you to run the original full duplex demo. Particularly, run it at like 1400 hertz instead of 19K so that you can hear computers beep booping at each other in all of their glory. It's kind of spectacular. But yeah, you want to have some time on your hands because it's pretty lossy. And so in order to actually get this duplex connection, I invented like the stupidest Byzantine fault tolerance algorithm in the entire world. And so what I did, instead of using the unambiguous encapsulation process for like header and payload, instead I just treated it as like 2 separate ways to encode 1s and 0s. And so what you do is you bark a tone, and then when your peer receives the tone, they repeat it in the other code, and then you flip back and forth. I tried to make a slide for this, but I just couldn't work out how to represent it in a way that looked okay in this size in Keynote. But I don't know, is that actually making sense? Because it's going to be kind of pivotal. Like, show of hands, who knows what I'm talking about? All right, awesome. Yeah, there are way better schemes. Kind of from the get-go, like I was actually really taken by the way Katie had kind of decomposed the problem and then like built it from the ground up in a fairly comprehensible way. So I was really, really loath to like grab some like, grab half the GNU radio source or grab some paper from someone that I didn't understand and just like blindly re-implement it without really knowing what was going on. In retrospect, I should have, because it would have worked a lot better. But it did at least have the advantage of being like really, really easy to debug. But the cool thing is, like, so normally you need to convert your data into a bit stream because you're transmitting it over something digital. But like audio isn't digital. So instead of like having 1s and 0s, you have the very real possibility of having 1s, 0s, and nulls. For example, if you're using like frequency shift keying, which is basically the process of like you take a carrier wave and then you modulate that wave. So typically what you do for frequency shift keying is like you'll have your carrier wave and then you will like slow the frequency when you want to transmit a 1. But instead of doing that, you can like slow the frequency for a 1 and speed it up for a 0 and then like treat the carrier wave as being a baseline. What this meant was, once I had like a pretty effective way of like timing where frames should start and end, bits that I wasn't sure about, I could just leave out and then let the Hamming weight sort it out. The error correcting code itself was capable of dealing with bits that I weren't sure what they were. So I spent quite a while on this. I got to the point where like it sort of worked in like really, really optimal conditions. And it was really cool, but like ultimately, my goal when I started this was I actually wanted something that would work walking down the street. And this, it was not, unless you walk very slowly in a perfectly silent, not vacuum because sound doesn't work so good there, but you would basically need to be in a place where you and one other person were the only person floating in no gravity. So I found this library called All the FSKs on GitHub. And as you may have gathered, this is about the point that I gave up on this whole understand everything I'm doing mantra. Instead, I was like, I'm going to take some working Python code and I'm going to bolt it to my thing. And so this guy published a library. It talks to PyAudio, which I was already using. It uses SciPy and NumPy interchangeably in ways that I'm not sure are actually legit, which probably explains some of the dramas that I have with it. But so I took this, I learned a real lot from it. Ultimately, I did get this working, but it was another case of the encoded data is so long that you will likely die of old age before you actually sync any data up. And so I concluded, yep, audio is still hard. But so this is the point at which, so up until now, I was still working on my full duplex solution. I was going to have duplex streams, damn it. But about this point, I realized that I was being unreasonable, and that was just not going to work. So instead, I thought, well, everything in the universe is immutable. When you add data to a graph, all you have to do is walk the new point backwards, and any of the points that are already meant to be a tip, you just remove them because they're reachable now. So why don't I just set up boxes that just shout the entirety of their databases all the time, go back to using the unambiguous encapsulation stuff to uniquely encode the headers so that it's very easy to tell when the header of a file starts, even if you're just walking in midway on the bit stream, and then just yell everything all the time forever, which is kind of like my discovery protocol anyway. And so this is what I was working on at 3 o'clock this morning. It works sometimes. The flip side was, so I actually went back to using Quietnet's code, but instead of using PSK31, which is a very aggressive encoding scheme, I took the same basic principle and I just stretched everything. So instead of using 2 zeros as the sigil, I use 4. To encode a 1, I use 3 ones, and to encode a 0, to encode a 0, I use 3 ones. To encode a 1, I use a jillion ones. I just leaned on the button. And then when I go to unpack the data, I basically there's a little bit of magic in it. All I have to do is heuristically determine whether or not this thing is likely to be a 1 or a 0 based on its length. And by sampling the first few bytes that I see, I can basically, for reasons I'm not totally sure of, the length of the bit streams that it unpacks tend to vary pretty wildly. But luckily, once you listen in on a stream for a few seconds, because there's such a wide difference in the length of a 1 and a 0, it's pretty easy to work out where you should draw that line in the sand. And they vary pretty wildly. I don't have a good demo for it, but typically, despite the fact that I'm intentionally broadcasting about 3 ones and 3 ones for a 0 and something in the order of 10 or 12 for a 1, I tend to get about 4 for a 0 and 27 for a 1, which actually makes it pretty easy to distinguish unambiguously. It's not rocket surgery at that point. Cool, so let's see whether or not anything better happened this time. So I mean, there's a lot of bit flipped bytes, a real lot of data. The upshot with this protocol is basically that because it's so aggressive, it's still just shoving these objects into the database pointlessly anyway. So all things going to plan, if I just like leave this running for the rest of the talk, it's going to come up. There is like a little, there's a log line that it spits out like when it successfully gets something plausible to write into the database that like looks like it might be a valid tip, which isn't in here. But like I've got 18 more minutes. This is totally going to work. I actually screwed up the ordering of my slides as well. This was my big plan for if my demo didn't go well. I figured I really like ducks. But so like what, while I was working on this, I picked up a bunch of really interesting tech. If nothing else, so I'd always known what like a Fourier series was at a very high level, but like I never actually had to do one. Definitely never had to implement one. So like I learned a bunch of really interesting stuff about like how to do FFT efficiently, especially in Python where arithmetic is kind of terrible. For the first time, I really like stopped to think about how to write a keying scheme. I work on things that are at pretty big scale at work, but like ultimately I was born in the like bandwidth is cheap era. And as a result, like doubling the size of something is nearly always not a real problem for me. In this instance, like I think the size of the database that I'm trying to move from this laptop to that one is something in the order of about 400 bytes, and we're 43 minutes in, and it hasn't gone anywhere. So it gave me like a bunch of context for like, holy shit, like trying to work out how to efficiently encode data is like a real problem. As well as just like some general context for like how to audio in Python. Like if you're ever picking up audio, like the PyAudio library turns out to be amazing. It basically knows how to do like pretty much everything you would want to do out of the box. The problem is digging into its insane and confusing API to work out why it's named something so totally irrational. But so like I'm assuming the question you're all asking yourself is like, holy shit, can I put my production data in this thing? I mean, Groundstation is like a thing. It's like 2 years old now. It's like I'm still working on it. If you have a problem that you like want to solve, or like if you have a hammer that you want to bash in with this nail, like by all means get in touch with me. I would be super excited to like work with you on it. And if nothing else, like I just like seeing my problems get adopted. Rad BIOS, as I'm going to release it, like I really wouldn't. I mean, play with it, but holy shit, like moving data around with audio sucks. And for anyone who falls into the last category, you're my hero and I'll buy you a beer. But so like instead, if you actually want to do things like this and have it work, there are a few other projects. So Kamal Mustafa wrote this thing called Minimodem, and ostensibly it does exactly what I want. It supports a bunch of like arbitrary keying schemes that include like various things that are like you have to use them on ham radio. It actually refuses to transmit anything without a call sign. It's also actually not as great as it's made out to be. Like, don't get me wrong, I'm not ragging on the developer by any way, shape, or form. But like the guarantees that the README makes about like what data you'll get out the other end and the actual data that you get out the other end are not strictly in line. So Linux has an AX25 driver in the tree. An AX25 is basically a packet radio format. It works really well over ham radio. I realize I keep going back to these guys, but the Byzantium guys actually had like, I think a 200 baud link over ham radio for a while that they were using to do something kind of similar. It does work really well. I mean, for the purposes of building something like this, it felt a lot like cheating. And also, like, it doesn't work very well at like audible frequencies, which really robbed me of my joy of wanting to hear a bunch of computers go beep boop. But in the Linux tree, there's also a module called Sound Modem, which does exactly what it sounds like. And so it's a layer 2 encapsulation format that uses audio hardware. I actually haven't got the only Linux machine with audio hardware that I have is a Chromebook. And I don't know if you've ever tried to build your own kernel for a Chromebook with some kooky module that wants to use non-proprietary sound hardware, but like, you're gonna have a pretty bad time. So I never actually got around to trying it. It sounds really interesting, albeit really chaotic, because yeah. They certainly imply that it will work with like more than 2 machines in the room, which I really just want to see or hear, I guess. And so like there are definitely some people I have to thank, a bunch of whom that I'm forgetting. But so Dominic and Mike for both releasing their unambiguous encapsulation paper and talking me into this ridiculous stunt. Katie for supplying all the code, which I then gutted and then reintegrated again. And Mark Jessup, who's the guy who wrote all the FSKs and also like responded incredibly patiently to some of my emails, basically being like, I'm drilling on myself, how do I audio? Cool, so like if you do want to get more info, I'm on the Twitter, you can definitely reach out to me anytime. I'd be more than happy to talk about computer things or this computer thing or whatever. Groundstation is up there. It has like a really stupid audio discovery mechanism in the tree that's currently up. I'll have this code like rebased and fixed up, hopefully tonight, definitely by tomorrow. And all the FSKs is like a really interesting library, as is Quietnet. Like you should definitely have a play with both of them, especially if like you're planning a stunt like this. Picking them up so that you at least get a feeling for the failure modes is really interesting. If nothing else, there's also a point at which like you do start to hear bad data and you realize that you might be in the matrix. And like Byzantium is just a really cool thing, and like I have a lot of heart for those guys. They also threw a lot of code at Groundstation while I was working on it, while they were integrating it, and all the bugs that I wrote were inconveniencing them. So I'm pretty glad of that. Cool. I think I timed this almost perfectly. Are there like questions, comments? Sure.
Yeah. Instead of FSK, have you considered Morse?
So the problem that the problem I had was never like, how do I encode the data? Like, at the end of the day, like once I had reliable transmission, you know, like encoding data is a very high level problem. The problem was very much like, how do I take like this bit stream that I do have and like successfully get it to the other end more or less unmolested? I didn't toy with Morse very much, because like, so at the end of the day, most of my payloads are binary. And so like anything that doesn't have, I mean like, so right now I'm actually using base64 and binary because the FSK I had basically has a full ASCII set and I can pack it into 6 bits, which yeah, it was kind of a convenient boundary for a number of reasons. I did toy with Morse. If nothing else, like I originally thought that PSK31 was Morse, but at the end of the day, like I'm still pretty confident that like how am I going to represent my data as binary was actually the least significant problem that I ran into. Sure.
Don't take this wrong. I, like you, hack things, and the journey, you're interested in something, and you follow it along, and by the time, you learn a tremendous amount. By the time you get to the end, you realize other people have somewhat attacked this problem from other areas or other domains and solved the problem. You mentioned PSK and FSKs and all. In the ham world, as some of this underlies, there's been a tremendous amount of work done to transmit digital data in very, very noisy environments. And you talk about a silent room versus a quiet room. Ham radio worlds operate in continually changing signal-to-noise ratios. I don't know if you've looked at any of the other encoding mechanisms or anything they use, but there's hundreds of pieces of software out there that you can run on a laptop and uses an audio connection to a ham transceiver and transmits data, very narrow bandwidth, very high reliability, in very, very noisy environments, and it's probably one of the fastest growing areas of ham radio. The guys running out here on the station are using some of those modes, and just think that's an area you might want to go look at.
For sure. I mean, like, it's a really valid criticism. And so, like, I mean, like, it's a very valid comment then. That's critical. So like, I mean, the point from the start was very much like I like wanted to build an interesting thing so that I'd know what I was doing by the end. And like, you're absolutely right. Like, this is absolutely a solved problem, which is most of the reason I'm like, for the love of God, don't actually use this. You know, like, so all the FSKs has an MPSK and actually like a bunch of really interesting like noise floor and signal to noise ratio instrumentation kind of buried inside it. And like I mentioned, like GNU Radio does more or less work if you're a wizard and you like wrote it. Yeah, I mean, that's basically the issue that I ran into was like most of the existing tooling that like does this extremely well either does it at like such a high level that it's magical and largely uninteresting for my purposes, or is incomprehensible and I just like spent nights trying to bolt it to my thing and couldn't work it out.
Well, you made me curious about going home and taking 2 laptops that I had, and instead of patching the audio out through USB into my transceiver, leave them on speaker and mic and see if they can communicate just by listening in the room.
Definitely.
I don't know, that's a good thought. The other one is you mentioned 19.1. I did a lot of electronic music in my background, and you always sweep the room because every room has got a sweet spot. And I wonder if that's another thought you've given this to.
Yeah, so my like amateur opinion, having screwed up this, so like I was actually kind of cheating. I was going to talks yesterday and I was sitting in the room and I was running this thing and traumatizing any dog in the vicinity, trying to work out like basically like what my best chances were of getting away with a working demo. Oh shit, my demo. Yeah, let's. I remember that guy. This is gonna be amazing. Cool. All right. So this is the thing called Airship that I told you about. This is, I can't actually see what I'm doing, so this is going to be, oh shit. Everything is bees. Okay, so. All right, so should have sensation. Come on. Yes! I did not anticipate that. So the best part is like last night when I was like toying with the demo, originally I had like a paragraph and like some markdown to show that it could do the fancy formatting. And then I started realizing like what the chances were of getting those extra 6 bytes from this machine to that machine. And I was like, yeah, 9 characters is heaps. Were there any more questions, comments? Sure.
I mean, just in reply to what he was saying, the project management team spent about 3 months trying to do that with the help of the ECM community. If you can get 2
Cool. Anyone else? Sure.
What would be, in broad terms, what would be the algorithm for probabilistically forgetting it?
Sure. So, I mean, you basically, so like Bloom filtering is the long and the short of it, right? You basically like take a node and then you take like a confidence interval, which basically represents like, it's basically like an educated guess about how many people actually exist on the graph. And so that's like awkwardly not the data graph, but actually the graph of like discrete people with databases. And then so you pick some probability that represents them. So like, I can't remember how to do the math off the top of my head. So for like the O of like 200 people, like 0.5% is probably pretty, 0.05, so like 5% is probably pretty reasonable. And then you just like delete that fraction of your nodes at random. And then you just like carry on doing this. This is basically like, I somewhat implemented it. There's obviously some stuff that you should do, like rather than just deleting at random, which is haphazard and also stupid because you wind up deleting like stuff in the middle and basically breaking your chains. So you should basically delete entire chains, and it makes much more sense to actually like look at the usage on the local node for like which stuff is accessed and don't delete that. But so, I mean, the general principle is basically just like exploit the way that random numbers tend to work. Just like delete some of the data at random and assuming that everyone's PRNG isn't DR, Joule, GR, ER, yeah, the backdoored one that I can't get the name out of right now, Julie C. Like everyone will delete different data, and provided that you have some mechanism of like subsequently querying your peers when you realize that you need something that you deleted, that's how you tackle it. Sorry, that was really waffly. Did I answer your question at all? Anyone else? Sure.
I wanted to know if the transport layer is more reliable at lower AKA audible.
Actually, significantly less in my totally subjective experience. Like I don't have like math, science, or anything apart from intuition to back this up. But yeah, the two reasons that I did this at such a high frequency for this were A, because it would be very difficult to talk over my computer beep booping, and the other one being that like while it was really satisfying, and if nothing else, when I just wasn't sure, like when I was trying to intuit which parts of my system were actually working, making audible sound made my life a lot easier. The mere fact that it like is in the audible spectrum just tends to mean that like more stuff in your house will probably collide with it, is like my intuition for why it was so bad. No.
If you had a clean line where you, instead of using speakers, you think the lower bandwidth would work better?
So I mean, like, are you talking like a copper cable or something?
Yeah.
Well, I mean, like, that's how we all got internet for a fair while, right? I mean, like, telephony is pretty well established. And, I kind of toyed with doing the so there was actually a really fascinating infographic the other day of like what the V92 handshake looks like, the like stereotypical 90s thing, which is like, I kind of looked at that and I was digging through it and I'm like, I'm sure there's a bunch of stuff that I can use in this. And then I was like, nope, this really assumes that you can move more than a few bits every second. Yeah, I mean, like, moving bits, especially across wire, even if it is kind of like encapsulated as audio, is pretty well backed anecdotally. That said, like, I mean, over like a sizable run, not many people ever did better than 56K. So in fairness, 56K is like several orders of magnitude faster than what I did. Yeah. In case you didn't hear, his question was, can I make the beep boop for a while? Sorry, 1 second. There's, like all good things, there's like a constant buried in the middle of a source file with like no configuration at all. Because I'm a professional. So this is basically what it was doing at like a much higher frequency. Yeah, I know what you were expecting when I said beep booping, but this is it. Yeah, I'm just going to turn it down a little. Were there any more questions? Cool. Thank you very much for coming out.